Of all the different types of rides that can be found at an amusement park, there's very few that can deliver the same terrifying thrills as a drop tower. These impressive machines allow riders to experience a straight freefall from dizzying heights, coming to a safe, controlled stop just moments before reaching the ground. This type of attraction packs a big punch given its small footprint, with the tallest rides extending to heights in excess of 120 meters, or 400 feet. Modern drop towers also come in a wide range of design styles with some clever twists that make them even more thrilling, including the most recent innovation of tilting riders forward so they fall face first. Despite all the variations that exist today, the original design concept for the freefall ride can be traced back to a single attraction that was built for the New York World's Fair in 1939. This ride was known as the parachute jump, and it consisted of a 250-foot steel tower with 12 parachutes suspended from a large frame with steel cables. Riders would hang below the parachutes in canvas seats that were hoisted to the top by an electric motor, and a drop mechanism would release them into a controlled fall as the parachutes slowed the descent. A similar type of wooden structure was used to train military paratroopers in the Soviet Union as early as the 1920s, but the technology was later patented in the United States, where it was modified for civilian use as a thrill ride. This ultimately led to the development of the first freefall type attraction, which was popularized by Swiss ride manufacturer Intamin in the 1980s, and they later improved the concept by introducing the first modern drop tower in 1995. Fast forward to today, and there are now many ride manufacturers that produce different variations of the drop tower. However, they all rely on one of two fundamental principles: either electromagnetism or pneumatics. The original design from Intamin employed an electromagnetic system, and we'll start by taking a look at this type of ride first. The tower itself usually consists of a cylindrical steel structure that is anchored to a large concrete foundation, and this is topped off with a machine room that houses the electric lift motors. Depending on the configuration, there may be a single ride gondola that wraps all the way around the tower, or there may be several smaller gondolas equally spaced around their circumference as shown here. The vehicles travel along rails that are fixed to the exterior of the structure, and each one is paired with a catch car that is mounted on the same set of rails above. The catch cars are suspended from the top of the tower with steel cables, and they can be moved up or down independently using the lift motors. When the ride is ready to begin, each catch car is lowered onto the corresponding gondola, where a mechanical latch automatically engages to lock them together. They are then hoisted up to the top of the tower, and when given the all-clear, the latches are disengaged to release the vehicles from the catch cars. After a brief freefall, the gondolas are brought to a safe and controlled stop by a magnetic braking system, which is both the most important and most innovative part of the whole ride. At the bottom of the tower, there are 2 rows of inert metal plates that run parallel to each set of rails, and these align with permanent rare earth magnets that are mounted to the ride vehicles. Each gondola has 4 strips of magnets, and they are arranged in pairs to create 2 thin gaps that are just wide enough for the plates to pass through. When a gondola drops down the tower, the moving magnetic field induces closed loops of electric current in the plates called eddy currents, and these generate their own temporary magnetic field that opposes the motion of the permanent magnets. The result is a magnetic drag force that acts on the gondola opposite to its direction of travel, which is similar to the repulsive force that you can feel when trying to push 2 magnets together with matching poles. The magnitude of the drag force is directly proportional to the amount of current flowing through the plates, since this determines the strength of the opposing magnetic field, and the amount of current is proportional to the speed of the vehicle. What this relationship tells us is that the braking force will be highest when the permanent magnets just begin to pass over the plates, and the force will decrease linearly as the gondola loses speed, thus providing a smooth, nonlinear deceleration. This method of magnetic braking is commonly referred to as eddy current braking, and it is used quite frequently in the amusement industry because it converts kinetic energy directly to heat without any need for moving parts or frictional wear. The system is also completely fail-safe because it does not rely on an external power source, and the brakes will still function in the event of a power outage. The only real downside is that magnetic brakes cannot bring the ride to a complete stop all on their own, since there will be a point during the deceleration when the magnetic drag force perfectly balances the force of gravity, and the gondolas will continue to move downward at a slow but constant velocity. In order to prevent a hard landing on the ground, the ride vehicles simply touch down on hydraulic cylinders that are positioned around the base of the tower, which absorb the remaining kinetic energy. Overall, this type of electromagnetic drop tower is a safe and dependable ride that is still popular today. However, it wasn't long after Intamin introduced it that American ride manufacturer S&S developed their own system using compressed air. These towers usually have a steel truss structure with a square cross-section, and the ride gondola travels along the four corners with small guide wheels, so there is no need for external rails. Inside the tower is a massive air accumulator, which is basically a storage tank that can hold air under high pressure, and it is surrounded by four smaller pneumatic cylinders called shot tanks. Each cylinder contains a piston that can travel up and down, and this is connected to a steel cable that exits through small seals at the top and bottom. The cable passes around a sheave at each end of the tower, where it then connects to the gondola, thus forming a closed loop around the outside of the structure. As the four pistons move in one direction on the inside of the tower, they pull the cables around the sheaves and drive the vehicle in the opposite direction on the outside. When the system is depressurized, the gondola will naturally rest at ground level while the pistons are raised to the top of the shot tanks, and this is how each ride cycle begins. Once passengers are loaded, a small amount of air is moved from the accumulator into the top of the pneumatic cylinders, which pushes the pistons down and lifts the vehicle. The ride computer then weighs the vehicle by measuring how much air pressure is required to balance it, and this determines how much air will be used to achieve the desired speed and g-force. Additional air is then released into the cylinders to lift the gondola to the top of the tower, where it locks into a mechanical brake that holds it in place before the drop. At this point, the accumulator is pressurized to its full operating pressure by moving air from an external receiver tank, which is paired with a large air compressor and drying system in a separate building. When the ride is launched, the compressed air in the accumulator is released into the bottom of the shot tanks, which shoots the pistons upward, releasing the holding brake and driving the gondola down towards the ground. As the pistons approach the top of the tower, the air in the top portion of the shot tanks becomes compressed, thus absorbing the kinetic energy and slowing the gondola down before bouncing it in the reverse direction just like a compressed spring. The pistons and gondola then oscillate up and down several times as the motion is dampened by slowly releasing air from the cylinders, and the vehicle is lowered back to the starting position once the system is depressurized. One of the benefits of using compressed air for a drop tower is that the entire ride is controlled by a single pneumatic system that does not require separate mechanisms for lifting and braking, yet the redundancy of having multiple cylinders and cables still ensures that the ride is fail-safe. The intensity of the ride can also be adjusted by varying the amount of air that is used for each launch, making it possible to achieve a drop that is nearly twice as fast as a freefall. The launch can even be reversed by releasing compressed air into the top of the shot tanks instead of the bottom, shooting the gondola up the tower with an acceleration in excess of 4 Gs. Regardless of the underlying ride system, electromagnetic and pneumatic drop towers both offer intense thrills that are unmatched by any other ride, making them popular installations at amusement parks all around the world. And while the experience of riding a drop tower may be terrifying, you can be assured that these rides are always designed with guest safety in mind first. Safety is the #1 priority at any amusement park, and the same is also true for today's sponsor, NordVPN. When you connect to the internet with a VPN, all your traffic passes through an encrypted tunnel, which protects your online identity by preventing third parties from tracking your online activities. NordVPN uses military-grade encryption protocols and never logs any user data, so your personal information always remains private and secure whenever you are connected to their network. In addition to security, a VPN can also be used to access online streaming content from services like Netflix and Disney Plus that may not be available in your region. To get around these geo-restrictions, you simply connect to a server in a country where the streaming platform is already available, and you can immediately access all the content as if your computer was actually located in that area. There are thousands of servers available with no limit on bandwidth, so you're free to enjoy as much content as you want from anywhere in the world. I highly recommend that you give NordVPN a try, and if you do it right now by going to nordvpn.com/artofengineering, then you can get 70% off a 3-year plan with a risk-free 30-day trial. That works out to just $3.49 per month, and for a limited time, you can also use promo code ARTOFENGINEERING to get 1 additional month for free. NordVPN is a powerful tool that keeps you and your data safe online, and they really helped me out by sponsoring this video, so please check them out by going to nordvpn.com/artofengineering using the link in the description. Don't forget to subscribe if you enjoyed today's video, and remember to hit the bell to get notified every time a new one comes out. If you are interested in supporting Art of Engineering and future projects, then you can also check out my Patreon page using the link below. As always, thanks so much for watching, and I'll see you in the next one.